Okay, and with that, as I mentioned, the technical theme for today is leveraging physics to secure energy delivery system. And this is a topic that is very dear to our sponsor. She's actually a PhD in physics, and one of the themes that we come back to is that you have enterprise systems and you have OT, operational technology systems, and the OT systems are subject to many of the same viruses and so forth that attack enterprise systems, particularly if they're networked, because many of the, particularly the control room workstations, run on commodity operating systems. The field devices are subject to different risks. But on the other hand, unlike in an enterprise system, you may have a good physical model of the system, and you can use that physical model and the measurements that you obtain from that physical model to reinforce your security. So that's the title slide in a long shot. Anyway, okay, how do you defend energy delivery systems? Measurement and control. Typically you have a control workstation and it's communicating with devices in the field. The devices may operate valves in an oil and gas systems, or they may operate breakers in a power system. So you're concerned that a cyber attack can interfere with controls, and this can cause overpressure condition, can cause line tripping, in extreme cases, safety hazards or environmental discharge or power outage, that kind of thing. But as I mentioned, you can sometimes, if you have a good physical model, use the physical measurements essentially as a side channel to give you the mechanism beyond what you can get from conventional cyber defense as you would see in an enterprise system. So kind of the question that we're answering is, are the measurements that I'm seeing consistent with the protocol? So this is a way essentially to define and constrain where and how an attacker can act using the laws governing the physical process. And if you characterize that, the defense strategy is to reduce the space as much as possible and then focus defenses on the rest. Focus defenses on the rest might mean, for example, that you have some degree redundancy in the measurement system, but the devices are potentially somewhat expensive, so you don't want to put them at every point, but you might be able to identify where they're the most valuable. So what's the physical model in an electrical system? Well, you have the Kirchhoff, I'm just writing the Kirchhoff current law and voltage law, and basically if you have a topology matrix where you have a number of electrical system components, the currents going around that circuit will sum to zero. And this can be expressed as a matrix equation, as I have done there in the first bullet. One property of many of these matrices is that they are fat. So that means that there are many solutions X that satisfy that AX equals 0. So one thing that has been known for some time is that an adversary can inject an attack that is proportional to one of those solutions and still satisfy, get away with bad data detection algorithms that are typically applied in these systems. That's called a data injection attack in power systems, if you want to research that. So how do you detect bad measurements? Well, if the attacker injects a change in the current measurement at a position J, and position J will correspond to a column in that matrix, then you kind of expand it out. You're going to get a non-zero element where S is the matrix product of the topology matrix and that change at that position. So if they can corrupt one measurement J, then that current change, the corrupted current measurement, has a non-zero element somewhere at some position, and what we call the syndrome vector, and that'll be apparent why I should call it that in a minute, is F times, in other words, the magnitude of the injection times that column J of A. And of course, we're engineers and we have to deal with noise. You may be interested in the sign or with some threshold and so forth. This is actually analogous to a Hamming error correction code and geometric single observer fault detection. So if you observe this condition, you're able to detect up to 2 and correct 1 for the matrix that we looked at. And what you can detect and correct depends on the size of the matrix. So what we're going to do is we're going to reconcile this condition with the observed protocol traffic, which is IEC 61850, very important modern electrical system protocol for configuring, defining, and communication in substations. And we're going to call it the agreement algorithm. So, is that it? Okay. On the left of this slide, we have the topology of our actual field demonstration. And you can see the little boxes. Those are actual ABB relays. We had an industry partner on this who has let us borrow, maybe donated these actual relays. And we did this at a substation on campus, adjacent to the University of Illinois campus. And yes, this is a field demonstration of this concept. We injected faults by bringing on large loads very quickly using heaters. And I'm not going to go through the equations on the right, but they are for this topology, they are with the Kirchhoff current and voltage laws that I spoke about previously. So how did we do this? So it's implemented as an error-correcting code. We derived the math, MATLAB simulation, and the system parameters were based on typical measurements, but not representative of any specific system, which can be a little sensitive. And that worked. Then we migrated to an emulation environment, what we call hardware in the loop, where we had actual relays supplied by our industry partner, real-time digital simulator. And if you're at Illinois, Washington, a couple of the other sites have these. These are something that can drive power equipment in real time for simulation, and you can design very complicated topologies in these. Very good thing to know. And if you're in Illinois, Tim Yardley and Jeremy Jones is in the room. And Prosper is also in the room. We'll get this started on RTDS. So we demonstrated in the lab the RTDS and then in the field. Good progress. Another approach we tried on the same circuit was writing these equations would have to be specific to the particular system. So can we do it with machine learning? And we used, for those of you who are interested, self-organizing maps and adaptive resonance theory. The hypothesis that we explored was, will these current and voltage laws lead to induced patterns that the system can learn? And then the normal operations and actual physical faults will obey the current voltage laws, but a false measurement injection, it's hard to do. You have to do it simultaneously, precisely, and at various points. So not to say that we're 100%, but what we like to say is we increase adversary burden. And this kind of go through the table. We're not perfectly there yet. The easiest case that we had, we did very well. We detected 100% of the attacks and had extremely low false alarm rate. Depending on how we stress the system and include or don't include certain faults in the training set, performance falls off a little bit. But the worst in terms of detecting the attacks is about 83% and 0 false alarms. So racing through it. How am I doing, Amy? Outstanding. Okay. So, leveraging, sorry if I feel rushed. So the point of these presentations, by the way, is if you're interested, contact the speaker, and they will be happy to provide you more information. But leveraging physics, if you have a physical model of the system that the EDS that you're trying to secure, it's an effective strategy, and you should look for opportunities to do that. If you have a research activity and you can develop that angle, our sponsor would love you very much. The specific project that we did was we derived a distributed agreement algorithm based on the Kirchhoff laws, and we demonstrated, stage increasing difficulty, starting with a MATLAB simulation, hardware in the loop emulation, and then actually out in the field. And then we're looking at the unsupervised learning approach, and to date we have demonstrated that in simulation, and that's it. So. In-depth question and discussion, please contact me directly. Otherwise, if you have something real quick, we have a couple of minutes.